Hi, today I want to calculate the uh, position and the diameter of the moon in a mirror system uh, that's a sphere or a spherical type surface. And we want to talk about that in terms of the size of the moon image uh, at the point of the sphere also. Let's read the question. Compute the position and diameter of the image of the moon in a polished sphere of diameter 20 centimeters. The diameter of the moon is 3,500 kilometers and its distance is 3,000 or 384,000 kilometers, and that's a long distance. So we're working here with some big numbers. The relationship between the focus and the image distance and object distance is important. But if we look at the picture of the problem as it's stated, we're ending up putting the image of the sphere inside of the sphere, which really can't be done, so that the answer will be in terms of imaginary and an imaginary image. The construction of these rays is such that the image angle is equal to the reflectance angle, and they point here to the focus of the sphere, which would be radius over 2. We can look at this also in terms of the observations of the mirror from an object at the radius of curvature to find out what the focal length of the mirror is. So 1 over the radius plus 1 over the radius is equal to 2 over the radius. So the focal length is equal to the radius divided by 2, which you see right here. The problem probably should be rewritten so that we can actually look at a more practical way to view this image. The image can be viewed if we in fact have half a sphere, or if we have a hole in the sphere such that the rays can get through to the backside of the mirror. And this way we'll get a real image off of a mirror. And again, the 1 over F is equal to 1 over R plus 1 over R if you put an object at the radius of curvature. The focal length is then d over 4, or 0.05 meters. That's a way to get the properties of the focal length of the reflective surface without actually knowing it to begin with. So if the moon is wide and we need to have an image formed at the focus, we can redraw this set so that we end up being able to look at something that looks like the image in setting up the problem. So our position of the moon in the sphere is 0.05 meters from the back surface of the mirror. At this point, we can see that the image distance is approximately the focal length of the mirror. So the image distance is equal to 0.05 meters. And we also know that the ratio between the image distance and the object distance is equal to the diameter of the image over the diameter of the object. That would be corresponding to m magnification equals minus I over O. We're actually demagnifying here. So if we do the mathematics, we have to be careful to put everything in terms of kilometers. And we have the diameter I of the image equal to the diameter of the moon over times the diameter of the image, the distance of the image from the mirror, and the distance of the moon from the image. And so we have here the numbers. We end up with 4.5 times 10 to the minus 7 kilometers. We end up with 4.56 times 10 to the minus 1 millimeters, or 0.456 millimeters in diameter. It's a very small image, but definitely is it's something useful and something that could be seen.